the whole thing was initiated by an action potential, and that's kind of all we said about it. Yeah, Valerie?
So aren't a lot of babies born with a heart murmur?
Possibly, I don't know what this, number is, but, that wasn't on my list.
I was just wondering what part of the heart would be.
Oh, that's the, mitral valve. What you're hearing in a heart murmur is that the valve isn't completely shutting, and, you know, you're hearing fluid leaking through the valve. And it has a sort of a murmuring sound. And sometimes I would imagine that might get, you know, remedy
A lot of
itself.
times correct itself, like the valve, I guess, the muscle will get
It,
stronger.
yes,
or something.
yes, and sometimes that might happen. If you had a severe, remember we said there was normally some leakage of the tricuspid valve. If you had really severe leakage, that also could be heard. And a whole bunch of fluid leaking through there. And that could really be heard normally. But it's the high pressure leakage that causes this more of the murmuring sound. So. Okay, so autorhythmicity. We're going to introduce a new type of sodium channel. Okay, and we're going to talk about depolarization and threshold and the whole thing that we talked about before. And remember, before we talked about a type of sodium channel that was a voltage gated channel. What caused the channel to open was significant change in the voltage. Basically what you had to do was depolarize the membrane up to a certain threshold, which would cause that sodium channel to open, okay? And then, if you depolarized it enough, a whole bunch of sodium came rushing in, and you crossed zero, and you then had an action potential, and that caused that sodium channel to snap shut. We're still gonna have those sodium channels, but we're gonna have a new kind of sodium channel that just leaks all the time, and that's all it ever does, okay? And remember, we talked about leakage channels briefly. They weren't significant in our discussion of how neurons work, but it turns out that they're very significant in this property called autorhythmicity, because these they're called slow sodium channels. They're a type of leakage channels whose leakage is significant enough to leak the heart up to its threshold. And that's what causes the heart to beat by itself, is you've got these slow sodium channels that slowly leak the heart up to its threshold, and that causes the fast sodium channels to open, the ones that we're used to, and then you cross zero and those sodium channels snap shut, and then potassium channels open, and it takes you back down, and the whole thing happens again. And these slow sodium channels are leaking all the time, so the heart, depending on the rate of leakage of the slow sodium channels, that will determine how rapidly, and every time you get an action potential, of course, the muscle is gonna contract, okay? And it's the rate of leakage of the slow sodium channels that determines how often the heart is gonna contract, okay? And the rate of leakage of the slow sodium channels is referred to as the pacemaker. And certain cells have slow sodium channels that leak more rapidly than other slow sodium channels. Okay? Oh, okay.
Sorry.
So these are examples of leakage channels. Okay? So here is, in this cell, this is cell B. Are the slow sodium channels leaking more rapidly or less rapidly than the previous ones?
Less rapid.
Less rapidly. The slope of the curve is less. And so this cardiac muscle cell would contract more slowly than the previous cardiac muscle cell. Remember, every time you get an action potential, that's what caused the calcium ions to leak in and bind to the troponin and all that stuff that caused the muscle contraction. So Each cardiac muscle cell possesses its own inherent pacemaker. The rate of this pacemaker depends on how fast the slow sodium channels are leaking. The cells of the atria possess faster inherent rates of leakage than those of the ventricles. So they're gonna wanna contract sooner.
We don't have, I don't have that slide in mine.
You don't have that slide?
No, and I've just downloaded it. It's
Well,
there.
what can I say? Wanna write it down?
Yeah. Yeah.
Pretty cool if you guys follow along like that.
I know, and I just finished downloading it.
Come up, take a picture of it, yeah, that's smart.
So the whole pace is determined by the slowest leak,
By the fastest,
by the fastest.
because the fastest ones are gonna beat before the slower one. The next beat's gonna be sooner than the slower one.
But then wouldn't that make it,
Well, you'll see,
okay.
we'll develop this as soon as everyone takes the picture.
Steph, can you send me a picture when it's too bright?
Just so everybody knows, I'm doing a video of the lecture this time, and I am gonna post the video. I haven't been posting the videos, I've just been trying it so far, but anyways, just so you guys know, I will post that video.
Good, good deal. Let's hear it. So, anyway, here you go, Tony. When two different cardiac muscle cells with different inherent pacemakers are touched, they contract at the faster rate. So, and that's because there's electrical communication between these muscle cells, we will see. And so, if you have a slower one and a faster one, they'll both beat at the same time to begin with, but then the next time around, the faster one will beat before the slower one, but that'll cause the slower one to beat too. Okay? So it's the faster one that determines the rate at which all of the cells in the heart are gonna contract, because all the cells in the heart are electrically connected to each other by little connections called gap junctions, which allow the cytoplasm of the muscle cells to communicate with each other, giving a sort of, it's like putting little electrical contacts between all the cells. So the part of the heart that normally possesses the cells which have the fastest inherent pacemakers, that part of the heart is the atrium, the right atrium. Yes, Valerie?
Is that like when you get a PVC on an EKG?
What?
Is that when you get a PVC on an EKG?
Well, we talk about all of that. We're getting to all of this stuff, okay? We're talking about a normal heartbeat right now. So the part of the heart which has the fastest inherent pacemaker is a little region in the right atrium called the sinoatrial node. And the sinoatrial node, you can't really, it's not an anatomical feature you can see, but it's a region, and it's in the right atrium, and it's called the pacemaker of the heart. And because of these gap junctions between all the cells of the heart, the action potential travels very rapidly through all the cells as initiated by the first one to beat, and then they all beat at the same time, roughly, although it takes a little time for the so-called wave of excitation to pass through the tissue. And this is actually good, because if you have the atria starting to contract at one point, as this wave of excitation passes through the atria, it causes them to contract from one side to the other, which ejects the contents of the atria smoothly out of them, okay, as that wave of excitation passes through them. And there are all kinds of funny pictures where they try and show pictures of gap junctions. And the one I like the best probably is this one there. So, desmosome just happened to be in this picture. But these gap junctions are little holes in between the cells that allow communication between the cytoplasm. And so you get a flow of electric current, you know, and remember that the cytoplasm is filled, has a bunch of dissolved ions, so it functions as an electrolyte and conducts an electric current. So these gap junctions are just like putting electric contacts between all these cells. So all of these muscle cells are connected by gap junctions. So if you connect muscle cell A, which was faster, with muscle cell B, which was slower, muscle cell B wants to beat slower, but muscle cell A makes it beat at the same rate as muscle cell A when you touch the two together. Okay. Get the idea? So it is the fastest cell in the heart that determines when the heart's gonna beat. Thus, all cardiac muscle cells contract as one, sort of. This rate is determined by the fastest cell. Okay? There are two nerves. Remember dual innervation of all the visceral organs? There are two nerves attached to every major visceral organ, a sympathetic one and a parasympathetic one. If you innervate the sympathetic one, it will cause the slow sodium channels to leak faster, thus speeding up the heart rate. If you innervate the parasympathetic one, it will cause the slow sodium channels to leak more slowly, and that'll slow down the heart rate. Okay, and so that's how we control heart rate. You can cut both those muscles and the heart will beat at a constant rate, as determined by the pacemaker, which is about 100 beats per minute. So you could cut both nerves, okay, and it'll beat at this rate. You innervate the sympathetic nervous system, it beats faster. Parasympathetic nervous system beats slower, because you change the rate of leakage up to threshold. Autonomic influences, what we just were talking about. So sympathetic speeds it up because that's fight or flight. Parasympathetic slows it down because that's rest and relaxation.
I have a question. If the fastest one determines the overall rate, then how does making the slow one leak slower slow down the whole heart rate?
You're slowing down the pacemaker.
Of the fastest one? Or?
Yeah.
Oh, okay.
Yeah. So this just shows the hookup, and the sympathetic one attaches to 3 places in the heart, and we're kind of jumped ahead of ourselves a little bit here, but this becomes more important next week. But we have, remember, thoracolumbar outflow is sympathetic, and craniosacral outflow is parasympathetic. So the vagus nerve sends a nerve, and then we have a sympathetic one coming from a thoracic nerve. Okay. So dual innervation. If both nerves are cut, the heart will beat at the inherent rate of the pacemaker, which is, if it's the SA node, that's about 100 beats per minute. There's certain hormones, like norepinephrine. If a person is in shock, he'll often administer norepinephrine because it causes heart rate to increase. It also causes the smooth muscles in all the arteries to constrict, which raises your blood pressure. By the same mechanism, norepinephrine allows calcium ion to come into the cells, causing them to contract. Cyclic AMP is the second messenger, and all that. Okay? Muscle cells in different regions of the heart possess different inherent pacemakers. Okay? So, muscle cells in the ventricles of the heart have much slower inherent pacemakers, and if you had to rely on the ventricles for your pacemaker, you wouldn't get enough cardiac output to live on. And so you would need then an artificial pacemaker. So this is the region in the right atrial wall, the sinoatrial node. Okay, so let's talk about the atrioventricular conducting system. How we conduct the impulse through the heart. The impulse is really just an action potential that it originates under normal conditions at the sinoatrial node. Okay? So here's the sinoatrial node up here, and it fires, and this wave of excitation passes down through the atria. Okay? And what I haven't mentioned yet is that there is a fibrous skeleton on which all the valves are mounted. It's not shown in this picture, it's hard to find a picture of it, but a skeleton made out of fibrocartilage. You need to mount these valves on something because there's so much stress applied to them. They would blow out of their, their fixtures if they weren't firmly mounted in something. And so all the valves are mounted in this fibrocartilage skeleton. And which books seem really shy about showing a picture. So you need to have a conducting system. It's kind of like a special system of wires, only it's not wires, called the AV conducting system, the atrioventricular conducting system. So we have the impulse initiating at the sinoatrial node, passes through the atria into this AV node, the atrioventricular node. It is stored there temporarily and delivered almost simultaneously to all the tissue of the ventricles at once, thus giving you a nice crisp ventricular contraction. Okay? It's almost as though, if you guys have ever heard of an electrical device called a capacitor builds up charge and delivers it all at once. Kind of functions like a capacitor. And so it stores the impulse for about 1/10 of a second and delivers it simultaneously down through the bundle of His, the bundle branches, and the Purkinje fibers, all of which you should know. Okay, this is all good cardiology. The cartilaginous skeleton prevents the impulse from spreading to the ventricles under normal circumstances, so we need the AV conducting system to import the impulse into the ventricle muscle cells. Here's a picture of this skeleton, this fibrous skeleton in which all of the valves are mounted. The 2 AV valves and the 2 semilunar valves are mounted in this fibrous skeleton, which is all well and good, except the impulse can't get through that. So that's why we need the AV conducting system. Okay, so here we see another picture of the SA node firing. The impulse passes nicely through the atria into the AV node, stored momentarily there and delivered simultaneously through the bundle of His, the bundle branches, and the Purkinje fibers out into the tissue of the ventricles. And so let's talk about the cardiac muscle cell action potential. Okay, we were looking at those crude little pictures before in an attempt to explain leakage channels. Now we're going to look at a little bit better picture. You may recall that a neuron, the length of an action potential for a neuron was about a millisecond, 1,000th of a second. Do you think that you'd like the heart to take about a millisecond contracting? Do you think that would work very well? 1,000th of a second? It wouldn't have any time to squeeze out its contents. Okay, in 1,000th of a second, no way it can contract that fast. If the action potential was that fast, the muscle tissue would kind of just be sitting there saying, what? So we wanted to slow this action potential down, and we have a way of doing that. We have our leakage channels, which leak us up to threshold. Then we have our voltage-gated sodium channels and voltage-gated potassium channels, just like before. But we also, in addition, have calcium channels that we're now become interested in. And with muscle cells, calcium channels are very important. And we see muscle cells have longer action potentials. It's not just a little blip, but you need your action potential to be long enough to develop a muscle twitch. Okay? And here's really about what it looks like. And so we're gonna go through this. Okay? What's not shown, because it's really kind of off the scale of the picture, and here we see our typical millivolts that we're used to looking at for neurons. Only this now is muscle cells. And remember, we talked about muscles before we talked about neurons. So I just kind of skimmed over this action potential thing. I said, well, we're gonna get to that real soon. And now we're getting, we're applying what we learned about action potentials and seeing how it's really involved with muscle cells, okay? And so we got our slow sodium channels leaking us up to threshold, and that opens the fast sodium channels, and boom, you cross zero and you get an action potential. That the sodium channels snap shut and the potassium channels open. But the moment the potassium channels open and potassium ions, remember sodium ions came in, making the inside more positive, and now when the potassium channels open, potassiums go out, making the inside less positive. But then you open these calcium channels, and there are more calciums outside than in, so you have positively charged potassium ions going out and positively charged calcium ions coming in. They kind of cancel each other out, okay? So that you don't get any net change for as long as the calcium channels are open. We have the so-called plateau phase of the cardiac muscle cell action potential. And this prolongs the action potential long enough that you can get a contraction, a full contraction, so that the heart can eject its contents.
So calcium is what makes it positive for the
So,
other
yes, calcium ion coming in is what gives rise to this plateau phase. You got potassium ions positively charged going out, positive charges going out, positive charges coming in, cancel each other out so that you get no net change in membrane potential, as long as the calciums are coming in. And then when the calciums quit coming in, the potassiums continue to go out, just like normal, and that repolarizes the membrane back to its resting situation so it can do it again. Okay? So if you take this part out, it would look just like a neuron, and it would only last, it would be just this little blip. But the calcium ions coming in for quite a while, okay, about 3/10 of a second, prolong this so that the heart muscle can contract and eject its contents. So this is another picture out of a cardiology book for medical school, which I really like. I didn't go to medical school, but a friend of mine did. And so anyway, this is your fast sodium channels. They open, the slow sodium channels leak it up to its threshold, and you have sodium ions coming in, and you cross zero, so that gets you up to here. Okay? You cross zero, and the potassium channels open, and potassiums leak out, and it starts to come back down, but that opens calcium channels, and calcium positive ions coming in and positive ions going out cancel each other out, so you don't get much of a net change until finally the calcium ions shut potassium ions continue to go out, and that takes you back to the resting membrane potential so that you can do it again. Okay? So that's a real good picture. Have you ever heard of a medication called calcium channel blockers? There are a number of them, and they just prevent calcium channels from opening as much, and that reduces the force of myocardial contraction, and it also reduces the tension on your arteries, both of which lower blood pressure. And they're used, Procardia was the first one, but there are all kinds of ones out there now. One called Norvasc that it was very popular, and it even went generic, and it's called amlodipine now. And it's dirt cheap, and it's very effective.
So blood pressure medicine causes the,
Well,
the heart
this
to
type,
be slower.
this type of blood pressure medication, calcium channel blockers. So there are all kinds of different blood pressure medications that work in different ways. Okay? And I can tell you about every one of them, and eventually will probably. So, phase 0, and cardiologists use these really strange designations. Why don't they call it phase 1? Phase 0 is rapid depolarization. The slow sodium channels leak up to the threshold, which opens the fast sodium channels until the membrane polarity is reversed. And then, okay, I suggest you might want to review fast sodium channels, but I can tell you guys don't need to. So then you have, that opens the potassium channels in a way that we're used to seeing, and you start to get repolarization, except then, once it starts to repolarize, that opens the calcium channels. Positive ions coming in cancels out positive ions going out. And so prolongs it so that you can get an effective cardiac output. Plateau phase, and the plateau phase is due to calcium ion. Okay? If it weren't for the calcium ion, it would just, the potassium channels would just take it right back down to 0 real quick. Cardiologists love to talk about excitation contraction coupling. Just rolls off the tongue so smoothly. It just merely means that the calcium ion, which is responsible for an effective action potential, as it comes in, also is responsible for the muscle contraction, because after all, calcium ion binds to troponin, and that exposes the binding sites and the cross bridges form and all that stuff. So the calcium ion that comes in is what causes the contraction. You may hear that term at some point. Repolarization is due to potassium ions coming in. And finally, you're back to your resting membrane potential so that you can do it again. Okay? So there's the picture. Okay. So the AV conducting system, okay, is really made out of modified cardiac muscle cells. Okay? You might have wondered, well, if it's not wires, what is it? And there's the AV node and the bundle of his, and the 2 bundle branches which go to each side of the heart. And the Purkinje fibers, okay? And you'd have to go a long way to find a picture of this either. Okay, the AV conducting system, constructed of modified cardiac muscle cells. It delivers the contractile impulse in a fashion which optimizes cardiac output. So the SA node fires, and that gives you your familiar looking action potential in the atrial muscle. But it reaches that skeleton and can't get through, so that sort of stops, but it goes into the AV node and stays there for about 1/10 of a second And then finally, the impulse is delivered simultaneously to the ventricle muscle, and you get that very familiar ventricular action potential that lasts long enough to give us a nice cardiac ejection phase. Okay? The impulse is delayed for about 1/10 of a second in the AV node. The fibers possess a smaller diameter here and conduct the impulse more slowly. So, let's look at EKGs. Why don't we call them ECGs? It'd be more proper. EKG sounds better, and you could always rationalize it by saying that in German, the German word for cardio starts with a K. So, anyway, that's my only rationalization. I prefer to say EKG, even though some people say ECG. So, let's learn about these ECGs and what they tell us. Okay? So each little square is 0.04 seconds. And so this little piece of paper runs out of this little strip chart recorder really rapidly. And they attach these electrodes to you in either 6 or 12 places, depending on how much they're charging you. And anyway, the first significant feature of the EKG is the P wave, and the P wave is registering the firing of the SA node, basically. Okay? So that's the first event of the cardiac cycle, is the pacemaker firing. And then we have the so-called PR interval. Okay? And this is the amount of time it takes to spread through the atria and be stored in the AV node. Okay? This is significant. All of these are significant. We will see. And the amount of time that they take is significant. So this PR interval is essentially, and you should know what that is, the amount of time that the impulse is stored in the AV node.
From like the P to the R?
Huh?
Like
From the P to the R. This is the QRS complex here. So this is just called the PR interval because it kind of goes from the P to the R. Okay. So then the most prominent feature is the QRS complex, which is the this is depolarization of the atria. This is depolarization of the ventricles. The depolarization of the ventricles covers up the repolarization of the atria. Then we have a delay, and finally the T wave, which people don't talk about so much, is the repolarization of the ventricles. They have to repolarize before they can depolarize again.